Thank you, Jonathan. Thank you for the invitation. I'm really very much honored by this. Of course, I would very much love to be there in person, but now this is the way we are communicating. So let's take advantage of that. So let me start with some motivation. This is a really high-level motivation. And basically what we try to do here is we try to use connectivity and automation to improve the safety, the energy efficiency, and the mobility of road vehicles. And we have seen many examples during this week for these. Many people talked about mobility. There were some people talking about safety, and there were mentions of energy as well, of course, and some of the talks focused on it entirely. So today I'm mainly going to focus on energy and safety, and maybe put the mobility a little bit to the background. So let me start with some categorization here. So about a year ago, I had the opportunity to work with some of my colleagues here at the University of Michigan, and we decided to write a review paper on connected and automated vehicles. And many things came out of this, and the final product was a paper in the vehicle system dynamics. But we also kind of thought a little bit about it, trying to clear, at least for ourselves, what do we mean by automated? What do we mean by connected, and what is connected and automated? So we came up with this little table, which you can see at the bottom, where really we distinguish between human-driven and automated, whether the human is in control or the computer is in control. Of course, actually, there are many levels of automation. So today, I basically going to put everything which is level 2 and above into automated vehicle, and everything which is level 1 and 0 into human-driven vehicles. And then there is another technology which is rising on the market, which is connecting these vehicles to each other and to the infrastructure. So currently it's referred as vehicle to everything, or V2X connectivity. And we can also categorize vehicles according to that. So there could be vehicles which are still human driven, but they are able to communicate. So they can share their position and velocity and can receive messages. And also for automated vehicles, it's possible that they receive messages from other vehicles. So they become what we call connected automated vehicle. And we deliberately left out the end between the connected and automated to emphasize that these vehicles have both properties. So I started to work on this topic maybe about 6, 7, 8 years ago. And at that time, we already had adaptive cruise control in high-end vehicles. So really kind of the way it looked in my eyes, that we just take one intelligent vehicle and we put it into the flow. And it turns out that already can be useful for the transportation itself, and already results something what we often refer nowadays as mixed traffic scenarios. And then Jonathan and others actually made very nice experiments where they actually tried to utilize this automation in order to improve the system efficiency. Now, in the meantime, we also realized that there is quite a bit of place here to kind of add connectivity to the system, but not necessarily increase the level of automation. So these examples, which I'm showing in the couple of few rows, you can see I still kept just one automated vehicle. Now I call it connected automated, but I start to increase, the penetration of connected vehicles. So the idea here is that the level of automation stays the same, but connectivity increases. Hopefully the system actually can perform better. And that was our goal with some of the experiments we did as well. And of course, you can increase the automation as well. And that's where, in my mind, people call cooperative adaptive cruise control. So if you have multiple connected automated vehicles, they are able to talk to each other, able to share the information, and they actually can can run their controllers in parallel, which of course gives rise to a lot of interesting opportunities and really high performance as a system. So today I'm going to focus in this middle part because I think that's where kind of we are at now, and want to understand what this technology can be used and how can we improve the behavior of the CAV, and how can we improve potentially the behavior of other vehicles around it. So when we started to publish papers on it, of course, we started with theory. So on Monday, if you listen to Aaron Ames' talk, he said, he always loves to do the math first and then put it into experiments. And I just want to emphasize there is, of course, a big contrast between the two, especially at the beginning. So when we started to write these papers about 5-6 years ago, we looked into all sorts of theoretical things, delay effects, nonlinearities, heterogeneity of the mixed traffic, including the driver reaction time, all the nonlinearities. So we had Lyapunov functionals, and also discrete implementation. So this sounds like really overwhelming. And at the end, when we started to do the experiment, we actually did something like this. Okay, so this is not trying to kind of just oversimplify things. Really, the controller we were running is essentially the one which you can see in this frame. Okay, so that was the first controller we ever built. And of course, you can see that the first part of it is really nothing else, just responding to the vehicle in front of you. So if you have a vehicle with ACC, essentially almost every ACC on the market is running something like this. Okay, the first two terms. The second term is very simple. You try to match your speed to the vehicle in front, okay, because you don't want to hit that vehicle or lag behind. And the first term is basically trying to keep a constant time headway. I mean, there are some saturations in the system, and for safety, we are not pushing this point to zero. But essentially, this is what physicists would call optimal velocity model, or what control engineers call an ACC controller. Okay, so the only thing which I added in this is this last term. Okay, so the last term is trying to do is that because of the connectivity, the vehicle have opportunity to receive information from the black vehicle, and actually we start to respond to the velocity of this vehicle. Okay, so this was this simple. Well, it sounds very simple, but once you start to build this controller and implement it on real vehicles, life starts to get a little complicated. So let me show you a simple example which we did at the University of Michigan. So we are really lucky that we have a test track called M-City, and we are allowed to test these vehicles there. So what you're seeing here in the video is a sequence of braking, and what you see is that the braking is getting harsher and harsher. Okay, so the first vehicle is already braking like -4, -5 meter per second square. That actually means that half of your weight is on your safety belt. Okay, so that's how you feel it. And finally, the human-driven vehicle, actually, you can see the pitching motion at the end. If I run the video again, it's actually doing 1G. So your entire weight is on this on the safety belt. That's a very harsh braking. Okay, and if you have, for example, not so good road conditions, icy, slippery road, you won't be able to make it. Now, once you start to add automation, so we basically did run the same thing, but simply running the ACC controller. After some optimization of these parameters, A and B, you can see that the acceleration of the automated vehicle actually goes down to like -5, which is still quite harsh. So if you do such a braking in real traffic, you would feel it certainly, but it's already doing much better than the human driver was doing. And finally, if you really run the configuration, which I'm showing on the right, you can see it's actually the vehicle is almost not braking. There's a little time when the brake light is on, but it's pretty much just gliding through the whole scenario. And if you look at the acceleration, it doesn't go below -3. It's around -2.5, which actually means you can drink your coffee when you are driving your vehicle, and you're not going to spill it. Okay, so we tested on the test track, and this was the simplest scenario we did. So our next step is, well, Michigan has beautiful roads. Let's take it out. Okay, so we found this beautiful stretch of a road close to Lansing, Michigan. It's a farmland, and it was really nice because it was about 8 miles of uninterrupted road. Okay, so there are intersections here, but this road always have the advantage, so other vehicles have to give you the way. And this allowed us to actually start to test this technology on real road. Of course, we wanted to be careful, right? So this was also a road where there was not much traffic. Actually, we made the traffic ourselves. Okay, so we only had 8 vehicles, and the big question was always that who should drive the Challenger here? Okay, because that was a V6 engine, and all the students wanted to drive that. But at the end, I think this guy here was the lucky one. He drove it the most. So what we did with this, we actually started to test those very simple controllers, again, just a few parameters and try to tune those parameters. After the tuning them on the test track and understanding that we are roughly safe. I will come back to how safe we are and how we quantify it, but it was good enough to kind of run on the road. And what we did was actually we just took these 8 vehicles and run up and down on the road, back and forth. And in order to kind of make it less boring, I was applying the brakes in the first vehicle time to time, which meant that I kind of produced these profile, which resembles somewhat, what you see in traffic, okay? And what you started to see is that basically as these waves propagated along the chain of the vehicles, they were amplified, okay? So many people refer to it as string instability. And indeed, we made many, many calculations before to kind of see whether our system is string stable or string unstable, but we could only ensure the string stability of the automated vehicle. So what you see here is that pretty much all the vehicles are increasing these velocity perturbations, but the blue vehicle is cutting back a little bit, okay? So this is roughly what you could do with ACC. Of course, there are other opportunities. For example, you can increase your time headway a little larger. If you keep larger distance, then it allows you to mitigate these waves more. But in this case, we deliberately wanted to keep it tight because what we found in other experiments is if you leave large headways, then people often like to cut in front of you. Now, I will show you some of the examples later, which we found on the public roads. So what we started to do, we started to add the connectivity, okay? And it shows an example that, once we add connectivity, the blue vehicle is doing better, at least with respect to the red one. And the more connectivity we gave, and we tried a couple of configurations. I think this was the most connected scenario, where essentially we were responding to 3 vehicles instead of just 1 vehicle ahead. And you can see an obviously cherry-picked scenario when we are doing very, very well. While the scenario is cherry-picked, we of course run this experiment many times and we check that indeed these benefits are there. There's something interesting you can start to see why these benefits is there. The blue vehicle starts to brake much, much earlier. So if you see the other vehicles, they are kind of repeating what the other is doing in front of them. They're just pressing on the brake harsher and harsher, while the blue vehicle is starting actually brake earlier. And that's what allows it to actually not to reduce the velocity so much, okay? So we published this work. And then while we were writing.
If it's all right, we have a quick question from Benny. Benny, I'm going to go ahead and unmute you. Go ahead.
All of this builds on the controller that you mentioned in the beginning. I'm not clear. What is U, the control function U? Is that acceleration or is it speed that you command?
It's the acceleration. Sorry, I was
okay, so it's second order dynamics. Okay, it's and then it looks like in the control law. So the control law does not explicitly exclude collisions, right? You're just adjusting your acceleration based to 3 speeds, so you don't have safeguards in there that kick in when you get too close or something.
You're absolutely right. So what happens is that I haven't shown you those safeguards yet. Okay. There are 2 ways to build them, and I will come to that later. But I'm just showing you the principal controller we were running. And indeed, safety is going to come up is like how we ensure it and how we make sure that this happens.
But in a nutshell, what you're doing is you take a sort of a weighted average, right, of 3 target, the optimal velocity function, and then the speeds of the vehicles ahead, and then you relax linearly towards those, right? That's
absolutely. That's simple. Yeah.
Okay, great. Thank you. Yep.
Yeah. So, and of course, if there are any other questions, I'm happy to answer on the way. So, so once we were actually writing this up, we found that one of the benefits, which we can see in this case, is originally we were thinking about, intercepting these traffic waves and really show that this has a effect on the transportation. Well, we still believe that it would be, but we only had 8 vehicles, right? So certainly this was not enough to kind of show these large scale effects. One way to kind of bring that out is exactly how you guys did, Benny, when you basically put it on the ring, right? So that's one opportunity to do there. In this case, we didn't do it because we wanted to drive higher speed. So this was a speed limit here was about 55 miles per hour. What we found is that energy-wise, however, we can see benefits not just from the automation, but also from the connectivity. So once we kind of compare the least connected and the most connected experiments we were doing. So the least connected is basically the ACC, and the most connected is when we were doing this average of the free vehicle speed. We could see, at least in this experiment, 19% of energy saving. Of course, the profile was particularly nice for this to kind of see these benefits. So we are not claiming that for every vehicle you can do this. But we also see something interesting, that even the vehicle which was driving behind the connected automated vehicle, this was also able to have some benefits in terms of energy savings. So we got really excited about it. And then we talked to some of the OEMs. And in particular, we started to talk to a truck manufacturer, Navistar, and they found it interesting, but they said, well, let's check it out because, you know, we have a little bit larger animals to deal with. And then they gave us this guy, okay? So without the trailer, this is 9 ton, okay? And certainly the power to mass ratio is much different from a personal vehicle, where in a personal vehicle, if you really command that acceleration, you typically get it if you are not on a very steep road. But that's not necessarily the case for the truck. The other thing is that because of this, you know, the engine control unit, we had to dive into that and really kind of play with a lot of things. It's amazing how complicated things are under the hood in one of those giants, okay? So what we wanted to do first is wanted to show that, well, some of these benefits, which we were claiming based on the single road experiment, somehow inherited to these large animals. And we were not expecting, of course, 20% fuel change just because we are driving differently on real roads. But our estimation was maybe around 5 to 10% improvement. So again, it's important to, yes?
Yeah, one question again, is the power to mass ratio larger or smaller than for a car for these trucks?
So power to mass is smaller, if I said the wrong way. I mean, power, so this has a 300 kilowatt engine, which is, I don't know, like 420 horsepower and 9 ton. Like your personal vehicle has about maybe 100 kilowatt engine, 150 horsepower, and then it has 2 tons, right? So this is really different. And once you put because these are not just built to kind of, for us to cruise with that, you know, once you put the trailer on, then suddenly you get 30 tons to pull. So it's really, you very quickly saturate and you can get into trouble if you do things quote unquote naively. So what we did with this, we actually run essentially the same controller, but first we were running it in simulations. And one of the things we found is that, well, we already collected some data with the other vehicles. Can we somehow utilize it in order to design our controller? Because if you go to Navistar, is that, well, you know, we just take your car on the road and going to play with it, probably they would be not so happy about it. So one thing we found is that there is an interesting way of optimizing these controllers. Basically, once you have traffic data, then you can actually run the controller in simulations and keep cracking up the data. Of course, it becomes very, very time consumable if, you know, we keep running it all the time. So instead, my students came up with a neat cost function. So we're supposed to basically somehow estimate this, what we call the energy function, this W, which is really nothing else but acceleration times velocity. So this is the energy per unit mass your vehicle is consuming. And this G function here is taking care of the fact that we are actually only adding the energy when we are pressing the gas pedal. When we are braking, then we are not using energy. So we don't have to add to the system. And they were able to show that this, we can actually upper and lower bound as a class K function of a very nice coast function. So that's we basically started to use as our coast function from now, which is simply based on the Fourier amplitudes of your response. So it's, of course, it's based on linear theory, but interestingly, it's very convincing that how much resembles the contours of this simplified coast function, which of course are beautiful elliptical. This is a linear system, and of course you can calculate all those Fourier components using some transfer functions. Compared to the real thing, in this case, is actually run through a high fidelity simulator of the truck. So you can see that, well, of course there are many differences. This is very nonlinear, And actually, in this case, we are talking about the fuel. So even the engine nonlinearities and everything is included. But you can see that, at least for this controller, it allows you a very simple optimization. So you can actually figure out, what these betas you want to put on your truck before you actually run on the road. So we found it very efficient. And of course, the method does work for any other controller. It doesn't have to be this super simple one. We basically just saying that we have a cost function, which is very easy to evaluate and really fast. And basically what you can do is that you can monitor the traffic in front of you, keep running, fast Fourier transforms on board. That's super fast. Even 20 years ago was very fast. And then basically you keep tuning these beta parameters on that, which you wouldn't do necessarily, every second, but maybe every 10 seconds or every half a minute. Based on how the traffic is changing in front of you, you can actually retune your controller, okay? And again, this is available for any other controllers, but we particularly tested it on this very simple one. So this was really promising, but we really wanted to test this vehicle on the road, and indeed, safety came up, and Ravi Star said, whoa, wait a minute. This is actually a 9-ton vehicle. You just can't just take it and drive it wherever, right? First of all, the person who drives it needs a CDL, a commercial driving license. None of us had that. And also they were just, this is not a toy, you just take away. So really we had to convince them that this is, testable on real road conditions. So that's where safety came into the picture, okay? So we'd run some tests with cars before in M-City. So you're seeing here one of the cut-ins. And these are one of those scenarios which we really wanted to get prepared for. Let me try to run it again. So it's hard to see from the drone video, but actually in this case, the white vehicle was running with 10 miles per hour and the black vehicle was running with 60 miles per hour. So it's 50 miles per hour difference. And it was very scary for the driver of the white vehicle because, someone coming with really high speed behind him, and he's supposed to cut in with 10 miles per hour. But we really wanted to test, whether with personal vehicles, at least we can ensure the safety. And turns out that personal vehicles are not that hard. I will show you what we can do. But trucks actually really need some extra thing to kick in. So there are different ways people approach safety, and I'm going to touch on 2 of them today. So one of them, which I'm going to spend the next couple of slides, is barrier functions. So if this is new, then I really recommend Aaron's talk, which he gave on Monday. Luckily, all the talks are recorded and online, and he has a very nice methodological explanation how to build this theory. And of course, he has tons of applications in robotics. Okay, so this is going to be one of the approaches which I'm going to show. Another approach, which I also going to touch base on, is formal methods. So this is coming from computer science, and you can see these kind of funny symbols here, which computer science are very much familiar with verifying codes. So then we also use this a little bit to improve the safety of these vehicles. And also there are people doing a lot of reachability calculations, solving Hamilton-Jacobi PDEs. I'm not going to touch base on that. So let me talk a little bit about barrier functions as it applies to this particular problem. Okay, so rather than in general, which again, Aaron did a good job on that on Monday. So first of all, in order to apply it, you need a model. It can be a very simple model, but it has to be some model. Actually, as a matter of fact, previously when Benny asked the question, maybe that's why I was confusing. I only showed you the controller, right? I didn't show you any dynamics. But here I'm showing some very, very simple dynamics. Again, the distance is nothing else but the velocity difference. The velocity derivative, so the acceleration, is the commanded input under some saturation. And this was the part which I was really hiding. So indeed, you will not be able to, make like 3G acceleration. Not that you want to have it because it would really hurt, but there's no way that you can do that in these giants. Okay, and also the vehicle in front of you, which is typically can be like a personal vehicle, it will also have some limitations of the acceleration. So basically, these acceleration limits, of course, can be different what the truck has, and trucks won't necessarily able to do like 1G deceleration, while the car in front of us may be able to do it. Okay, so this is kind of the setup, and really what comes from barrier function theory, it is kind of qualitatively and quantitatively evaluating safety. Okay, so basically what safety means in this sense, that we want to stay in certain part of the state space, and the state space here is your velocity, the leader's velocity, and the distance. Okay, and in particular, what we say, you want to be above a certain surface. I mean, you certainly want to be above 0, because that's really when crash happens. But with some careful thinking, you can realize that maybe you want to keep some kind of time headway, which is this 1 over kappa. And you will quickly realize that there is a section of state space where you won't be able to maintain it. So that's why this kind of other part of the surface, which is coming up here. And what the barrier function allows you is that once you define this barrier function, again, basically, you use a function to define which part of the state space you would like to stay at. Then there is a theorem which allows you to basically test any controller, and in this case, it's already written in the control barrier function setup. Then basically you take the derivative, the lead derivative of this function, and also, well, this could be a little more general, but here I just use the linear class K function times this barrier function itself. And this is really the same one-dimensional differential equation which Aaron brought up on Monday regarding the Lyapunov functions. Okay, so why is this good? Well, they can do two things. One, you can take your controller and test it. You can see, is it a safe controller or not? The second thing is you can actually synthetize controllers, which allows you to intervene when your controller becomes unsafe. Okay, so let me try to show you how does it work for the ACC. So honestly, the parameters you want to run, for example, in this nominal controller are these gain parameters, alpha and beta. And you really want to have them below 1. So the reason is because once they start to reach 1, then people start to fly in the car. So it's really, the worst happened with us on one of the test track. Luckily, the student who was flying was a judo master, so was able to roll in a way inside the truck that he didn't get injured, okay? So that was really lucky. But you don't want to go into these really high gain scenarios. But what it shows in this case, that at least for the truck, the feasible parameters where you want to be at, and the safe parameters where the safety condition actually holds, they are really disjoint from each other. For a personal vehicle, they can overlap. With a little bit of tuning and playing, you can actually bring it. So what it means that for a personal vehicle, you can select an alpha and beta that even this very simple controller is provably safe, okay? So that's right. But for a truck, basically, there's no chance, okay? So the only way to do it, to really do control barrier functions, and what it means is that at some point you need to switch to a safe controller, okay? So again, I'm keeping this nominal controller, the super simple one on the left, and you can see this more complicated one, which is on the right, actually. And this controller actually is the one where you're going to switch to if your system feels unsafe. Now, unsafe doesn't necessarily mean you're already touching the bumper of the vehicle in front of you. Unsafe is going to be quantified using the control barrier function. One interesting thing you can see here is the acceleration of the leading vehicle appears. So that's a very nice application of V2X connectivity, because it's very hard to get that from velocity derivatives and so on. Typically, it's a good idea if that is transmitting the vehicle to you. The vehicle is transmitting to you what is the acceleration, and that allows you to switch. And actually, after you solve those QPs, Aaron talks on Monday, it's basically just taking the minimum of the two. Okay, and it works really nicely. So we tested this on a test track. So you can see here that this is when we actually crushed the truck, but it's already unsafe way before it's actually getting close to the crash. And once, of course, you let it go, eventually it hits the other vehicle. So we were playing with here, okay, we didn't want to die in that little minivan. So what we did is we were running in different lanes, but the connectivity allowed us to actually still run these tests. Actually, if you don't have connectivity with sensors, you have to have dummies and things like that. So it was really nice that we didn't have to do that. And if you switch to the scenario when you turn on the control barrier function that it actually allows you to stop in a safe distance. Okay, so this is a really big difference. And once we showed it to Navistar, then they started to maybe trust us a little more, that maybe we can take this vehicle to the railroad. So I really think that, barrier functions have way more applicability in automotive control than this very simple one. But we are very happy that at least we were able to show that, we can make these systems provably safe in experiments, right? So that gap between theory and experiments is not always that little. But in case of barrier functions, it was really nice because we basically needed one more line in the code, say, if this happens, switch to this. So that's a pretty a simple way of coding. We didn't have to solve online optimizations and so on, complicated things on board. So now let me show you another video which we recently captured in one of our road trips. This is down in the south. That's why the weather is looks nicer. So what you see here, there was a vehicle who actually came and cut in front of us. It's a GoPro video, so it's not that close, but trust me, this was close. Actually, at some point, the safety guy who was driving the truck with the laptop, he was really having his fingers, whether it's the vehicle is going to have a really harsh braking. And in many cases, actually in these cases, we rather disengage because barrier function is going to save you, but you don't necessarily want to apply it all the time, right? So it would be nice if we could handle these scenarios with some other methods, right? So if you really think about it, there are two vehicles here. They are kind of competing for the same place. If they know in advance what the other guy is doing, they might kind of sort it out. So those decisions, especially if they have connection between each other, it can be done before. So basically, we don't have to get into the scenario when it becomes a safety critical issue, right? So in order to do that, we started to work on something what we call conflict analysis. So first, we tested it on an MCD. So the blue car is just driving constant speed. The other is really trying to come in. You can see it was not successful at the end, actually hit the cone. So it was a pretty close call at the very end. That guy was a race car driver, so he was able to push it. But you can see that it's not obvious for a long time whether he's going to be able to make it or not. At the end, he was not able to make it. Turns out, just with slightly different initial conditions, he actually was able to squeeze it. So it's a good question, how to make these decisions, and you don't want to make it at the very end. I mean, then it's, of course, your barrier has to kick in. You have to keep the system safe. But can we make these decisions a little bit earlier? So this is, again, what we refer as conflict analysis, and we start to do it with a very simple scenario, which is this merging scenario. So again, this blue vehicle is trying to merge, and the red vehicle is just traveling on the main lane, and we define the conflict zone where we don't want these two vehicles to be at the same position or in the same zone, because that we declare to be potentially unsafe. So again, we need a model. The model, again, is very, very simple. It's those second order integrators. My student, How, really like this inverting the distance, because he says that it's better to kind of measure the distance from the conflict zone rather from some other kind of vantage point. And that means that we have these negative signs here, the distance versus velocity, but we made sure that everything is still fine, so we didn't try to reinvent Newtonian dynamics. And here is maybe the key concept here. So basically, you can define conflict, as I said in words. We don't want the two vehicles to occupy the same space, with some logical operators. So basically, you can say what the position of one vehicle and the position of the other vehicle should not do. So this is actually the conflict. So that means that this would say that the two vehicles indeed occupy the conflict zone at the same time. And luckily, we can break it down into two different pieces. So because there are two options. One, you go first. Two, you go second. I mean, this is a very simple scenario, but we believe that even in more complicated scenarios, we should be able to break it down, okay? So what it means is that we can actually also write down the logical formulae that a vehicle 2 merges ahead of the red one, or vehicle 2 merges behind of that one. And you can mathematically prove that P and Q is actually nothing else but not having C. Okay, so if either, sorry, not and, or, so if either P or Q satisfy, then we can avoid the conflict. Okay, so there is a proof for this, right? So let's see how can we somehow make it computationally feasible that this thing works. So we started to create this, what we call conflict charts. Okay, so the idea is that now we have two scenarios. Why don't we just kind of craft these charts for both of them? And to explain what is happening here, so again, this is the scenario when V equal 2 is supposed to merge ahead. This is a state space cut, okay? So it's R1 versus R2. In the AP region, it doesn't matter what does the red V equal to do, you can always merge ahead, okay? In the yellow regime, it does matter what this guy do. If you're lucky, then you can merge ahead. If you're unlucky, you might not be able to merge ahead. And in the red region, it doesn't matter what you do, you will be in conflict. Okay, so there is no controller here which could avoid conflict based on these simple models, of course. And the scenario that we are only looking at the longitudinal dynamics. Now you can do the same thing for the merging behind and create a similar chart. Okay, so again, what it means, green means whatever the other guy do, you can still merge behind. The red means that doesn't matter what you do, there's no way that you can merge behind, and the yellow is this kind of middle region between. So once you put them together, and this is what we refer as a conflict chart, then you start to see what actually people often refer as a bad SAT. This is the red one here, okay? So this is actually where you don't want to be here, okay? That's really bad. The yellow one, well, it's also not so good, right? You can be unlucky and then you won't be able to avoid the conflict. You really want to stay in the green region, okay? Now, people have been calculating these regimes, again, using reachability calculations before, but what is interesting here are these arrays which are coming out, okay? So what it means that these are our decision-making boundaries, even though if you are, say, 125 meters from the conflict zone, where a human would be not able to make any decision whether I want to go ahead or want to go behind. Even our race car driver screwed up many times, even though he had a good idea, how powerful those vehicles are and so on. So at this point, we can actually use these boundaries to make a decision. Okay, so that's something which we haven't seen before, that there are these, again, these are some kind of manifolds in state space, emanating essentially for these corners of the conflict zone, as you can see, but they stretch out and we can actually use them in order to make nice decisions. So let me show a simulation. How does it work? So this is a scenario where we're actually merging behind the other vehicle, okay? And if I show you the animation here, so these manifolds are moving, okay? But again, this vehicle used at the beginning, they determine this is not a safe scenario. I don't want to go for it, and basically just goes after the other vehicle. In this case, actually, the red vehicle is real data. So that's real highway data, okay? Now, if you look at another scenario, when the vehicle merges ahead, then again, what happens is that here, it basically started to see early on that he can make it, and actually that's how it was able to do it, okay? So very early on, it made this decision, and again, connectivity is essential. When these simulations start, the two vehicles probably don't see each other by no means by any camera or any sensor. There are concrete barriers, bushes, all sorts of elevation issues there, but connectivity can actually penetrate that. And again, they're actually not negotiating, right? So this is even simpler. You can imagine, for example, that the red vehicle is just a human-driven vehicle, which was in case of the data, and the blue vehicle is an automated vehicle. So it's simply just receiving those messages and try to make this decision. Sure, you can do more and you can make them talk and you can make it more complicated, but we think that as a first application, it's a good idea to start this way. Now, I need to wrap up really soon, so let me come to some conclusions. So again, we started with some high-level societal goals, and we tried to take those goals and translate them into the control objectives of connected and automated vehicles. So that was kind of where we started. We said we want to save energy, and eventually we ended up with certain optimizations. We also found that connectivity can help to achieve these objectives in a sense that it can make an existing already well-working system more efficient, or it can give you capabilities which you don't have with pure automation. And finally, we found that there is a provable way to deal with safety, okay? You can use control barrier functions in order to ensure the safety when you're getting close to the safety limit. But you can also use temporal logic to actually make decisions that are very, very far from the safety critical scenario. So you basically don't even ever get into that safety critical scenario. So my last slide is this one. I just like to thank all the people. Currently, we are collaborating. There are, I mentioned a lot, Aaron. So we have an active collaboration with him, as well as Richard and Joel at Caltech. There are some people at Budapest. They are my academic brothers, if you wish. And we also work together with Clemson University, Ardana Vahidi. And Rose, you just moved to UCSD very recently. So we have some collaborations with her. We are also work with companies who are interested in some of these things. The main sponsors are Navistar, Toyota, and Ford Motor Company. And here at the bottom, you can see this is my group, basically. And obviously, most of the results are coming from them. Today, I mainly spend time on Howe's research and on Arnold's research, but some other people's research also taps into this. And at the bottom, you can see a couple of colleagues from Michigan we have been collaborating with, and it really makes it fun. So with that, thank you very much for the attention, and I'm very happy to answer any questions.